Yes, sir, you can start. If you are okay, sir.
Yeah, just now we had 9 to.
I'll take just only a few seconds, like a little bit introduction about. I have already.
Relax and take time. You will start, sir. Because you are
Yeah,
so much busy all through the
I
day.
just came from office with we had a program from morning to evening from geosynthetics and dams. So
Yes, sir. We
as
can
per our
understand,
meeting.
sir. So just
Is it visible?
yes, sir, your screen is visible.
Oh, Professor
Yes, sir.
Arindam is here.
Geosynthetics
Yes,
and
I have
infrastructure.
come to listen to you.
Oh, this is very simple. I thought
Good evening, sir.
Good evening.
this is a
Sirs,
normal, simple thing
sir,
that which normal. I would be covering about geosynthetics, then the principles of reinforced soil and
Krishna
factors
recording.
affecting the reinforced soil
Yes,
behavior.
started.
Fundamental, simple thing, which I think may be required for some of the youngsters. That's the only thing.
I am also youngster, sir.
No, you are okay. You are young.
So,
And in fact,
it,
I should say that we had a very good workshop on use of geosynthetics and dams for 2 days. So we had just completed and came back, so that's it.
yeah. So I will contact you and Doladi very soon.
Yeah.
She
I spoke
called
to
me.
Bharat. Yeah, correct. I spoke to
Yes,
Bharat also yesterday.
yes. So
Tomorrow
me
I'll
and
be
Bharat
meeting him.
spoke.
Yeah. Okay.
So we will tentatively finalize the thing and we will come over a video conference to
Right.
discuss.
That's great. So good evening. Let me start in the Sheikh. Okay.
Yes, sir. Yes, sir.
Okay.
Yes, yes.
Let me just start this lecture, and I would like to cover 3 things. One is the use of geosynthetics and reinforced soil structures, and essentially, I would like to tell you about the varieties of geosynthetics and products that we have, and the principles of reinforced soil. That's very essential. How this geosynthetics and reinforced soil principle play a behavior or play a good
Sir,
complement. Yeah.
sorry for the interruption, sir. I think the screen is. I mean, it would be better if you could do it slideshow.
Okay. Okay. It's okay now?
Yeah. Yes, sir.
Yeah.
Perfect.
Okay. Good evening. Again, I will talk about geosynthetics and reinforced soil structures in this class program. And let me tell you that the geosynthetics are a very wonderful material, and we'll be talking about some introduction of these materials, their applications and transportation, geotechnical, geoenvironmental, hydraulic engineering, and private development as well. This is something very interesting product that we should discuss because this is a polymer. I'm not sure. I'm not able to show them, and I'll see, but I'm not able to get those products to your hand. In a normal class, we'll distribute all these materials in the class, and then try to get a feel of feel of those products. But then we'll see them here. What is their background, polymeric background, the types of geosynthetics, what are the functions, design methods, and application areas. And these geosynthetic materials are nothing but polymeric materials. Okay, like we are aware of polymers, which are C molecules of C and H. Okay, carbon and hydrogen molecules that I think most of the materials are that only. And these polymers or a chain of molecules, we call actually monomer is a simple structure of C and H. We call them as polymers because it's a chain of molecules. And you can prepare, so for example, what you see is a plastic sheet that we see is a polymer. So some of these materials, like, we talk about polyethylene, polystyrene, PVC, and all of that, we call them as polymers. And they are essentially taken from they're essentially from the particularly in the processing of the materials from natural gas and bitumen and all of that. So you get in the form of a resin and to form a resin, and then there'll be the form of flakes, and we try to add certain additives because to see that they have some properties that we need, and we formulate new compounds, right, to have some strength and stiffness, whatever properties we want, and manufacture them so with the suitable processes, and they result in a particular geosynthetic material. So we have varieties of materials here: geotextiles, geogrids, geonets, geomembranes, geosynthetic clay liners, geopipes, geoforms, geocomposites. And this is a typical example. I think some of you must have seen these products. Geotextiles are in this form, which are actually, we know normal textiles, they have certain thickness, certain mass per unit area. Like, you go to maybe in Assam sari, it could be a 200 GSM or 100 GSM. They have so many varieties of materials in natural products, like even you have a jute fibers, and you convert them into jute products. They can, with some thickness, some weight, they are, and then make them into some engineering applications. They are going to be useful. So many of these geotextiles, if we talk about them, they are all from polypropylene fibers. They use, of course, standard textile manufacturing processes. We have we divide them into woven, or then again in this oven form we have slit film, monofilament or multifilaments. Nano-ovens, we have needle punched or heat bonded, and they have geotextiles are having certain open structure and a porous structure. This is to suit our applications. Okay, they have certain mechanical properties and hydraulic properties that we need to have testing done, and they're very, very versatile in their primary function. Their primary function that we'll see that they are useful, we'll discuss them. These are all geogrids that we see, geotextiles. These geogrids are, again, useful products. You can have mono-oriented, like their strength is oriented in one direction, or the other one is the bidirectional, like, the strength is distributed in two directions. So these geogrids are something that, they're also quite useful. They're again they're all from unitized own yarns or bonded straps. You can see the strap material. They allow for soil strike through, like, essentially soil also can interact through because there are openings there. And as I just mentioned, bidirectional, equal strength in both the directions. This is required in some applications like bearing capacity and all of that, like wherever there is a loading into two directions, both X and Y. And we need this bidirectional strength. Whereas in a thing like a retaining wall, you need a unidirectional strength. So that's in one direction, you will have more concentration of strength. And it is essentially on reinforcement applications, whereas geotextiles is in separation and filtration functions. And these materials are used for walls, steep slopes, base, and foundation reinforcement, as I just said. If you want to improve the bearing capacity of a soil, maybe it's 10 ton per meter square, and you want to make it 20 ton per meter square or 25, you can make it. Or if you want to construct a reinforced slope, maybe normally we are used to 30 or 35 degrees or 40 degrees. You want to make it 60, 70, 80, it's possible. So this is geonets. Again, these are all another products that we see. They're all again made from high density polyethylene, and the results in a parallel sets of ribs as an integral unit. And there is a flow, there is a, more of a, there is slightly the, hole there in that pipes type of thing, a small pipes type of thing. You have biplanar and triplanar, and always in-plane drainage. When you try to put in a horizontal way, the drainage occurs through the pipes. That's very interesting thing. And they're all covered. We cover them usually with geotextiles. We use them in conjunction with geotextiles because geotextiles are normally used for separation function, and to some extent, they can serve the function of the drainage as well. But if you need more drainage area, we'll provide this geonets. And so with both geonets and geotextiles, geocomposite, and they're very, very useful in road applications. These are all geomembranes. You can see they're all, their application is more in terms of barriers. Like you don't allow anything here. It's like, say, for example, you want to do seepage control at the dam or any dam, right? We can do that. That's a very good material. These are all, again, as I said, force is always containment. Like they do not allow, it's a barrier to both liquids and gases. Like particularly in landfill applications, we use them a lot. Of course, in dams, we use them a lot on upstream side. So for example, you want to store the water, but you don't want the water to percolate through the embankment. So you try to line the whole upstream side of the dam with this geomembrane, and it's very, very helpful. So some of these materials are manufactured in rolls, and they're all required in many applications in waste containment like landfills. And there are a lot of applications in hydraulics wherever there is a seepage control. All of that, it's a very good application. We have geosynthetic clay liners. Again, this is another product where we have two geotextiles which are there in between the geotextiles. They have bentonite powder, and this is another interesting product that can be used in varieties of applications in landfills. In fact, I have been using these materials for water retaining structures because, as I just mentioned, instead of the geomembrane, I am using this as well. And then even whenever people want a clay material, clay liner, we are using this material because it's quite versatile and better than clay liner. So this, again, the function here is that it's always a containment. Like it'll store or whatever liquids it has. It doesn't allow anything, barrier. You can say it's a barrier. So the product in between the two geotextiles is a bentonite. And sometimes some of these products can be needle punched, means with some reinforcement can also be done in the form of stitches or some fiber, some tension members, like, punching is done through some wires, and stitching is also done. And the bentonite product is bonded to GM is also available. There are many products that it's a very versatile material, GCL. It has a sodium bentonite, calcium bentonite, and India is great in some of these products because a lot of bentonite is available in the country, and lot of preparation of the products are made in India. Actually, it's not made in India and exported elsewhere. This is one geosynthetic materials or one thing that government is talking so much about make in India. But in geosynthetic industry, a lot of things are made in India, but we don't use them much. Then we use many people from Europe and US use that because the costs are cheaper here in India, and they are very good. As I said, they normally we use compacted clay liners in landfills, and they are very, very attractive when you try to compare them with the geosynthetic compacted clay liners. So GCL is much better. In fact, I use it quite a lot. And they're also good in geomembrane geomembrane. Okay. Geopipe, actually, the term can be any material, but the moment you try to use it in underground or in soil applications, we add the term called geo, so that many people take ownership, right? Like a geotechnical professionals can take ownership that, yes, we try to see how it fits into the geotechnical requirements. So geotechnical requirements for the geopipe are nothing but buried pipes. So for example, geopipes can be used in many applications of landfills, like it's a plastic pipe and it's more like a drainage that either it can be a contaminated liquid or anything. High density polyethylene and PVC are the most common, and sometimes they can be smooth. So there's a lot of this growth of this geopipes. The applications are many. We have geofoam, like seen some of this type of material, packing material we enter in, like we call it as geofoam, and we use it behind the retaining walls and all of that. This is a very good material as well. So it's a volume is more light. It's a lightweight fill, and like it's a lightweight fill on soft soil, or so that the weight on the soft soil is less. And it's also slightly compressible, so the lateral pressure in the retaining walls can be reduced. There are a lot of applications also used for insulation of frost-sensitive soils. So then geocomposites, as I mentioned, two products, like one is a there are two functions in some of these materials. Like one can be, ideally there are 5 functions to start with, like a separation function, filtration function, drainage function, reinforcement function, moisture barrier application. So there are 5 functions in general that we try to talk about in geosynthetics. And so if you're trying to combine 2 functions, like one can be a filter and one can be a membrane. So like this can be useful in dams where you put this geomembrane is required so that the water is not allowed, but at the same time, the drainage will allow that, whatever is collected beneath the membrane, it gets drained into certain, at the bottom of the dam. You can provide a pipe. You can call it a geopipe or whatever pipe you want with some perforation, so that the drainage capacity you have to calculate properly from your seepage and flow net calculations. Okay. You can put on the, say, for example, the upstream side. You can put it and then drain off all the water. Okay, all the seepage pressures are reduced. You can provide on the downstream side also. We call it upruns, right? Horizontal upruns at the bottom in the dam sections. That's one thing. And landfills and many other applications, you can do that. In some roads, pavements, we have both reinforcement function and drainage function. Because in roads, that whatever we see in roads, if they are of poor quality, and if you want, and then you need to have a lot of aggregate to be used, say for example. And if you want to reduce an amount of aggregates, geosynthetic materials can be used by reinforcement function or even the separation function. And drainage also can be facilitated by the geotextile. So if you're using both of them, you can really specify 2 products. One, and you have a material here, which is a geocomposite. So they are all varieties of products here, a combination of geotextile, geomembrane, as I said in the case of a dam, or geotextile as geogrid in the case of a road, or geotextile as geonet, again in the case of a road or something, it can be done. And it's a very, very interesting product. And see, the thing is that we need to understand which is the main function and then the secondary function. They say, for example, in the case of a dam, the primary function is moisture barrier. We don't want water to go through, and I don't mind putting a geotextile there or a drain there. So but drain can puncture a geomembrane. I don't want to take a risk, so I put a geotextile or some other layer which can remove the water from water that is collected next to the geomembrane, right? So like that. So primary function, secondary function needs to be identified in a particular thing, right? So these are all some, as I mentioned, like separation function, reinforcement function, filtration, drainage, and containment. So if you look at this, geotextile can serve a lot of functions, like it can separate the various layers. Say, for example, in an embankment or in a road, particularly you have subgrade, subbase, base course, wearing course. geotextile will definitely help a lot. If you put on the top of a subgrade, it will really, help a lot. And it can also serve a reinforcement function. It can do filtration and drainage to some extent. Main thing it does is a separation, to some extent filtration. Third one, if a lot of rain is there, it may not be there, but to a limited extent, it can do drainage also. And it can also act as a reinforcement function if there is a, depending on the subgrade strength and all that. Okay. If the soil is very, very poor, definitely geotextile can also work as a reinforcement function. So geogrids, it's only for reinforcement, but it's a specific application, right? They're made for that. Geonet, it's a drainage. Again, it's made for drainage. Geomembrane, it's just made for containment or barrier applications. Geosynthetic clay liner, it's a barrier application. Geopipe, a drainage. Geoform, a separation, right? And geocomposite, yes, you can combine all of these functions and then club, mix and match, and you have this product. Okay. So what are the design methods? Okay, so this is a very, very important thing that we should understand. The based on the cost, of course, when you're using these materials, what is the advantage that you're getting? Like, is it a cost benefit? So we must be able to understand the design principles. Like if I use a geotextile or a geogrid in a road project, I must be able to do a cost analysis that without geogrid or with geogrid, how much is the thickness of the road construction for 1 square meter, right? So maybe something will cost you 500 rupees normally, and with geosynthetic, it could cost you 400. Whatever. I'm just giving it tentative numbers. It can be even, say, for example, 1,000 rupees, and it can be 800 rupees. So whatever. So per square meter costs, it depends. One has to evaluate depending on the places and transportation distances. There are many things that are there in the cost evaluation, but that's one thing. The cost is based on their material supply, and of course experience matters, availability matters. That's a very important thing. And the second thing that we see is a specification. Okay, like this is another important thing that people say that we know that these products are helping. We have seen that all these geosynthetic products are very, very helpful in most of the applications in civil engineering. So when you say that, people know that, okay, you have a specification, like, use a geotextile in this application, or they don't need to really understand the fundamentals of it so much, but it's required by specification. So you have to use it because people have seen that there is it's very useful. So for example, if you look at solid waste management guidelines, Government of India, SWM, right? New rules came last month, 2024. We have been following 2016 guidelines. They will say clearly that use composite liner in the liner in the landfills, or use this GCL, like when you have less clay, like that. They say that. In fact, that's what is called specification. So it's very clearly they specify what should be the thickness, what should be the product type, and they mention. And it's for the common routine applications. Even one can say for road work, you can use by specification. So when it becomes more standard, we can put them. But the best would be that you try to understand the function of each of the materials, right? If you are able to understand this function, then you can calculate. So for example, you're looking at reinforcement function, or you're looking at drainage function. So you try to identify the product, and then the critical nature of that application. Say for example, in Northeast we don't have good aggregates, and aggregates are not available, which will suit IRC specifications. So it's critical that we use geosynthetics there, because they reduce the volume of aggregates there. So definitely then you have to have a design which is made by function. The function here is that reinforcement application, right? How does it help? Or separation function if it is a geotextile. So we can really do this. So we use, how do you get this design by function is that, say for example, there is a loading of 50 MSA, million standard axle load on a highway, or 100 MSA, something load. So you need to calculate what should be the design strength for the material, tensile strength required for a geogrid, right? So that we call it as a required design property. Like I can say that the geogrids have certain tensile strength. Then what is allowable? You have a tested, so you go to a particular thing and you can do the design, and design gives you, say, for example, 10 kilonewton per meter is the number that we get. So now we have a product that people are ready to supply at some 40 kilonewton per meter, or 50 or 60 or whatever, 100. So that could be divided with a suitable factor of safety to get the allowable value, and then so that becomes allowable property, and the required design strength is what you calculate from design. So you can design by function. It can be for any application, whether it's a retaining wall or many other applications. Okay, so a lot of test methods are available, and there are testing labs in the country. Design models from literature are available, and the factor of safety application is it is application specific. Like I can have a factor of safety in different factors of safety for different applications, right? That's one thing. Any doubt here? Hello? Any question? Okay. I hope people are listening.
Yeah.
Shaikh? Okay, because I'm not able to see anything. So application areas, there are many, as I just mentioned. Transportation and geotechnical, like we use geotextiles, geogrids, and all of this material. Okay. Geo-environmental, hydraulics, private development, we are using all of these materials. One statement people make that in civil engineering, we are all only used to soil, concrete, steel, something like that. But we know about maximum people. We know about a lot of people know about concrete, and to some extent steel, less steel. And then third is in soil. Of course, we don't know much. Rocks, we don't know much. Even geotechnical engineers also, we have a lot of difficulty. But then we have a lot of problems in most of these things. Like even hydraulic engineers, they know more about water flow and all of that. And environmental engineering people know about contamination and contaminant migration and all of that. And transportation, geotechnical people, they know about pavement design, retaining wall, and all of that. But in all of this, they're not really, you don't have suitable soils, you have a lot of problems in many of these things. To solve some of these problems, the geosynthetic materials are very, very ideal alternative. Okay, like in transportation and geotechnical, people have been using very, very well, and they're cost effective. All these geoenvironmental, hydraulic, and all of that, they're so useful. We'll discuss that. Say, for example, transportation geotechnical applications, we can use geotextiles as filters. Okay, as I just mentioned, that they can be as separators first and filters to some extent. And geotextiles and geogrids as wall reinforcement. Yes, in a retaining wall, if you want to do a retaining wall, RE wall design, you have to use geogrids. And even the geotextiles and geogrids can be used for slopes. And we have what is called the big drains. Okay, PVDs. Okay, it's a geocomposite. Actually, geocomposite has both the drainage and the PVDs are used for soft ground improvement. And in soft ground improvement, we need to have both the drainage and filtration applications. And so geocomposites will do very effective job there. And we have a lot of erosion control applications, particularly, I'm sure that, in Northeast, Professor Arindam Day and many others are involved in a lot of applications, and that I think they will be able to cover. I'm not sure, but I know about it. So the geotextile filtration is something that's a very interesting application. This is in soil, in geotechnical engineering, filters are required. Means they allow the water, but the soil loss should not be there. So when you're using a filter in geotechnical engineering, say for example, dams or roads, right? They should have three requirements. One is that adequate flow. The material should allow enough flow, and proper soil should not be flowing. So this is what we do in a conventional design, filter design, that we have adequate flow. At the same time, soil can be retained. Then long-term flow equilibrium. The other things that we want to ensure is that steady state conditions are there. Okay. These are all for that. And of course, there are in fact, I gave a lecture on seepage in dams yesterday for an hour. So, but then here we are only talking about for a minute or two here, that filters in dams, drains, the pavements are very, very essential. And the application of the filter is that it should allow flow of water, but you should not, the soil particles in the filter, the base soil, you are trying to put in the case of a dam or a road, the soil particles should not be lost, because if the flow is little more, like if the hydraulic gradient is more, there is a chance that the soil gets lost through the filter, which we don't want. So these are all, we use a lot of filter applications in retaining walls, erosion control systems in slopes, pavement drains, okay, like this, right? We don't want in a pavement, you put a pipe here, all down the pipe, here we can have a geotextile here, right? So whatever is the water that comes and gets collected here, you have a perforated pipe here, and whatever is the water that can get collected, it can enter here, and then the geotextile will filter only only the water. That's important. So you can use in some of the applications in this manner, right? You can see that geotextile being used for the pavement drainage. Wall reinforcement. This is a very important thing, that maximum applications of there. If you see a lot of flyovers in the country, they use geosynthetics, and they have the wall design has number of elements. Say, for example, a retaining wall design. We know that retaining wall, say, for example, a gravity retaining wall or a cantilever retaining wall, it should have sufficient factors of safety in bearing pressure, then sliding and overturning. That's what is a conventional design. So we do that, whether it is a reinforced soil wall or normal wall. But since we are using geosynthetics to reduce earth pressure, or nullify the pressure, earth pressure, to take care of the pressure, I should say, we use geotextiles or geogrids. So when geogrids are being used, the length and spacing and phasic connections need to be done. And as I said, external design needs to assess overturning, sliding, and bearing. And we also use some reduction factors on reinforcement, because, say, for example, you want a 100-year guarantee from a product. Like retaining walls are designed for, say, 50 years or 100 years, right? So that 100-year, the values that use for strength in design needs to be reduced, corresponding to mechanical damage, creep, then durability. Factors that will come, that depends on you have to test the material, then apply these factors. Okay. Then sometimes we use overall factor of safety also. Sometimes that's another thing, which is to resist the unknown, like global factor of safety, or as a matter of abundant caution, right? This is an example that I can mention, that in a retaining wall, normally would have got for a cantilever retaining wall, but when you have a geotextile, this technique is called wraparound technique. Okay, where they say, for example, height of the retaining wall can be anything. Normally in roads it will be 7 meters or something, but Now we have the walls of even 60, 70 meters. Like you can see here, this wall is about, this could be about 10 meters, 10 meters, 10 meters. Like, it could be total height of this system could be 30 meters. Of course, there are some steps here, but then the total length can be, 30 meters. Okay, like that. The important elements that in design is that we know that this is earth pressure that we use, earth pressure diagram that we use. Okay, this will be the pressure due to surcharge. Okay, like Ka gamma H. Okay, like earth pressure and the live load pressure. So there are three components if you are trying to design a retaining wall for a highway. You have to consider the design has to consider the pressure, the surcharge load, like then the live load, right? Surcharge could be about 2 meters, something like that, whatever D. Then all of this combined pressure, lateral pressure, needs to be registered by the reinforcement that you provide. Hello, Mini Mall is there. Hello, great, nice. I think I'm talking very simple things. Mini, you are going to cover which topic?
Yeah, I'm covering, sir, but definitely your introduction will help me a lot.
Okay, fine. I just want you. That's fine. Okay, I thought I'll three. Yeah. So, thank you so much. Okay.
Yeah.
So the thing is that, yeah.
Ma'am will cover sustainable geotechnical engineering. Okay, sir.
Pardon?
Continue, please.
Okay, it's all right. Come on. See, this is all sustainable geotechnical engineering only. Okay, everything is sustainable geotechnical. All of us only talk about that in a single voice, but it's now three voices. It could be myself, Madam, and Arindam, all of us. Okay, right. So the issue is that when you're trying to do the design of a retaining wall, we need to come up with a proper spacing and the length. Okay, so this earth pressure, which is there horizontally, it's acting. The total earth pressure that we say sigma H, which is a combination of three pressures. One is earth pressure, then the earth pressure due to lateral, surcharge pressure, and the live load. And there could be dynamic loading as well. There could be many other. The surcharge can be some hill load or anything. It can be anything. So you need to convert them into a horizontal load or horizontal stress, and we try to see that force is resisted by the geogrid by friction, right? In the interface friction between the geogrid and reinforced soil. Backfill soil is a critical element, and we try to provide this geotextile. This is actually a wraparound geotextile, and geogrid we use to take care of that with adequate factor of safety with respect to both tensile forces and tension as well as pull-out capacity. If you're able to do that, your design is complete, and you have both spacing and everything is covered. So the design codes are there covering that. I think even they may be able to cover all of that. So yeah, you can have varieties of retaining walls, right? I think, okay, tired retaining walls and many other things that we have here. So reinforcement of the slopes, very, very interesting application. Like normally we were trying to provide 2:1. This is what we see in most of the cases, but people can go for very, very steep slopes as high. It can be vertical as well. So again, we use geotextiles and geogrids to increase the slope angle and the height. And except, you need to take care of the erosion. And it's an excellent method. People have been using it very well. Like there's some of the applications like this, right? And big drains are a prefabricated vertical drains. Just I mentioned that if you are trying to improve soft soil, maybe in, say, for example, I think Paradip and many places, they have a lot of applications, many soft soil areas in the country. They are doing this technique. And I think Madam and others will cover a lot on, they have done a lot of work on this. And so prefabricated vertical drains allow for rapid consolidation of saturated fine-grained soils, because the problem with the clays is that the coefficient, the consolidation times are longer, and we want to reduce the consolidation times. Instead of 5 years, we would like to make them to 6 months, something like that. So one can really, you have a geotextile where the geotextile is a filter and you have a drainage core. It's about 100 mm wide. It's a very small one. You see all of this out of the ground, and they're all small, about 100 mm wide and very thin, like 2 to 10 mm thick and 100 mm long, like I mean, it can be 10 meters, 100 meters long. Okay, so it can be very long. Okay, they come in rolls, right? And so the designs are well established. A lot of case studies are there in India, particularly even in Odisha. The erosion control systems are there, many, like, so these are all some products that one can use. A lot of products are there. Okay, slope protection, and we use that for channel protection. For all of this, there are temporary applications, permanent applications, and you have soft, where it can be applications in terms of that laying and all of that. Okay. When it comes to geo-non-engineering applications, there are many, like landfill liner systems, cover systems, vertical cutoff barriers, liners for surface impound ponds, liners for heap leach ponds. Okay. The problem of waste is something very big in the country. Like, I'm sure that, so for example, per person, a person generates 300 grams per kg. And if the population is 10 lakhs, it could be 30 tons or 30 tons of waste per day. Okay. So where does this waste go? So, for example, in Bangalore, with about 6,000 tons per day. Mumbai, maybe 10,000 tons per day. So the waste problem has been big, and to handle that, we need landfills, and we don't have proper landfills. So we try to dump them out. So the lot of moisture, the rain will generate a lot of waste, leachate, and leachate is something very problematic. And there are a lot of problems in the country because of this landfills. So to really mitigate the problem, we have what is called, we use bioreact. It's a more barrier concept, which means that we want to isolate the waste. Okay, isolate the waste so that it doesn't affect the atmosphere by 3 pathways. The pathways are that it can be, say for example, the methane emissions from the landfills can pollute the air. Leachate from the groundwater can, leachate from this landfill can pollute soil as well as water, right? So all this, the problems with soil, water, and air are preventable by using proper products from Geosynthetics. So how do you do that is something that we'll see here. That, as I mentioned, you have a geomembrane, like you have a geomembrane, you have a GCL, you have a geonet, so all of this, you have a pipe, leachate collection pipe, all of this can be done. And then on the top of it, it's a design one has to do, considering a lot of factors that that is specified in codes. As I just mentioned, that some of these things are mentioned in the solid waste management guidelines. Okay, just as I said, recent rules are there. Last month they were released. You can see that on what are the applications that one can have. How geosynthetics can be used in varieties of applications mentioned there. So for example, remediation of dump sites, can we use it? Can we use in any other products? That is there. It's a very good document. Okay. So as I said, geomembranes, first basic level that they do is that they need to have a bottom liner in which we use a clay liner, but clay liner alone is not sufficient. So we use a clay liner plus a geomembrane. Okay. So the clay liner and geomembrane, we call it a composite geomembrane. And we have a lot of design methods and all of that here. So we call it actually sometimes in hazardous waste landfills, two liners may be required. One is a primary composite liner, and the second one is secondary composite liner. I just show you this diagram, like it has a two double liner systems here in this case, right? So, but in normal municipal waste landfills, one system is sufficient. But in hazardous waste landfill, it's a rule that they should have a double layer system. And most of the industries which have hazardous waste, say for example, in places like Odisha or even Gujarat, where a lot of industries are there, they use it. Okay, many places where it's there. And one thing is that, like, there are a lot of advantages of use of these products. Of course, here GeoNet is used. And the products of the Geosynthetics products, like one can use more layers. And if you're able to have more layers, it's more better. And in this case, in 9 layers are used. Say, for example, in the previous slide, you have many layers. You have a geogrid for reinforcement of the slope. Okay. Then you have a geotextile, you have a geonet for drainage, you have a GCL, you have a geomembrane, you have a perforated pipe, geopipe. So if you look at it, the numbers are quite big and good because you want good performance. The main thing is that, in fact, many people ask me, so you're using a lot of plastics, right? That's one obvious question people have an issue. That, but then the plastics actually you're using for environmental benefit. Here, the beauty is that plastics per se are used in an efficient way, in an engineered way, in using geosynthetic products. And even some of these products could be recycled products. There's no problem with that. And so world has recognized this. And by using properly the geosynthetics, you can reduce carbon emissions better than without them, right? That there are two cases. Do nothing, like don't use geosynthetics, and use geosynthetics. If you compare them, the greenhouse gas emissions that you can control or reduce will be much, much higher in the case of using these products. That's one thing you should realize. Okay. So these are all some applications. So when in a landfill, after the complete filling is done, it would take over a period of say 15-20 years. You need to put a cover. Cover will have again various layers, like at the top of the waste, I don't mind putting a gas collection layer, and I don't mind I'll put a geomembrane. Why? Because I don't want methane to go out. See, sometimes the biodegradation process is so time taking. I may say 10 years and close it, but the biodegradation is still active, and I don't want methane emission from the cover. So you can take the methane emissions out. You can put a geomembrane, you can put a drainage layer, you can put, if you want, a reinforcement, so in a cover soil. All of this are possible if it is particularly a steep slope, and you can have a geopipe, all of this. So there are varieties of applications are portable, and this has become very necessary in landfills. Okay. Okay. So this is how it is, say for example, somebody counts how many layers can be used in a landfill, like base liner 9, waste itself 2, and final cover 7. There are many layers one can think of, because all these things are being done to really see that there's a proper performance from this. We don't want contamination. That's the most important thing, right? So the other thing that, in fact, there's a very, very crucial application, and we don't have proper contractors for doing this type of work. Even today, I was talking to somebody, there are contractors who can do this cutoff walls. The cutoff walls are nothing but that, suppose you think of an abandoned dump. The abandoned dump can have a lot of leachate, and there will be nearby groundwater. It continues to pollute. So now I want to stop that pollution. So I must have a slurry wall, slurry walls are normally made of bentonite slurry or soil cement slurry, and so many products are there. And if, say, for example, a dump site, say, is in Bangalore, there are cases where it's 20 meters deep, and I must be able to construct a slurry wall of at least 25 meters, which is not there. In fact, such technology we are searching in India, it has not been there with proper, I mean, of course, somebody says that they can do it. That's what I also have some confirmations, but they need to talk to the local authorities where, they need to, should be cost effective as well. Okay. So it is very useful in a lot of contaminated sites to see that the flow of contaminants is stopped. And it's very better, very good if you have a geomembrane. That's what it means. You can, if you're able to put the geomembrane into the slurry wall, that's a great thing. That's it's very attractive, and it's really solves most of the problems, at least in some sites I know. Surface liners for surface impoundments is another thing, and like you want to collect water, right? That's one thing. So it depends again on the lot of design parameters are here that I can show you. Like, say, for example, you don't, when you want to store water, or it can be a water, or it can be a leachate from a landfill, or it can be a waste liquid from a company. They can't be just arbitrarily left alone. So they need to be stored in a proper container, and we need geomembranes and all of that. So you can see all of this here. And this is actually a failure of a product. You can see all the wrinkles here. This is in the case of a double line hazardous waste pond. And sometimes there is a problem of vein formation, that the geomembrane can get lifted up, and then it can form what is called veins. Appear particularly when the load due to the leachate is less. The contact between the soil and the geomembrane is lost, and since the overburden is not much, because it's almost in a dry condition, it's half empty, or maybe not much liquid in the leachate pond, so it gets it just comes up. That's one problem. So here you will see somebody trying to measure the or look at the leakage detection. Right? So the in landfills there are a lot of applications. Okay, and in mining there are a lot of applications. Okay, particularly in that's what I find that the biggest applications are in mining. And if you want to store the mines, the mined waste, ideally the mined waste is also very, very problematic. So you need to have proper lining systems, cover systems, and all of that. Now the rules have become very strict in the country. So yeah, these are all some applications. You have any questions here? There are many, of course. So we are able to cover, of course, even they can be used in a household level. If somebody was telling today, I mean, it's well known that if you want to have a roof garden in the house, you can use a geomembrane at the top, and then have the roof. That is an application. Yeah, tell me.
I have a little doubt. Do you think a number of layers in a landfill is always same, and that is which you mentioned 18, including?
No. It is, see, this is a very, very optimistic projection. Okay, you don't need all of them. Okay, you need to really. Okay, if you try, but then you have to use, normally we go by minimum. Okay, minimum is that it depends on the type of problem that you have. Like, we need to have liner, then you need to have a filter, and you need to have the top of the waste, waste collection between the waste. As a separator, you should have a geotextile. There are many, you can reduce them a little bit, but if you're able to justify their use, I think it's great. They're
And
useful.
also, I think there might be some governing factors.
Yeah.
which can influence the number of layering, like climate
Correct, sir.
condition, weather condition,
Correct, sir.
how much
There are many
rainfall.
things, right?
Yeah, yeah,
No, this is
many
a projection by the geosynthetic industry, okay?
yes.
Not me
Okay.
and you. This is essentially that you have to justify everything, design. You know, for every product, there are calculations, right? All should be, if you are able to convince the client, show that this is necessary, it's okay. And this is a cost benefit. You must be able to show three things. You know, nowadays, people want, like LCA, life cycle analysis. Like if I do a LCA analysis of a dump site, I mean, waste landfill using this and normal. See, there are two things. One, you just follow blindly normal specifications, you'll get some carbon emissions. But if you use all of these products and see, you have there are a couple of things like leachate collection can be made better. It can be recirculated and all of that. There are a lot of systems we have. So you need to show that which is the most optimum. You must be able to identify with different alternatives. Yeah.
And also when you thought that cross-sectional of final line cover system,
Yeah.
I saw that you are starting from geomembrane, then
No, first layer I would suggest would be that
foundation layer.
Yeah, so on the top of the geotextile, on the top of waste, you should have a geotextile layer. Okay.
Okay.
I mean, because then you'll have what is called, the waste itself, you try to put anything on that, it becomes waste. So better to put some geotextile so that it serves. And then the first is the gas drainage layer. Okay, if there is a gas drainage there, if any gas is there, it can be collected. Okay, but if it is a fully stabilized waste, like you can take waste samples and you can find out what is called biomethane potential, right? There is a test that you can do. And if the biomethane potential is there, then you can put that. Otherwise, no, right? You have to justify that. Then the second layer would be that I go for a geomembrane because I want to harness all the methane, I don't want to methane, whatever residual methane is there, I want to take it. So that is there. So you need to do some arrangement. And after that, I don't mind putting the clay liner or a GCL and or a drainage layer. After that, the thing is, yeah, we need to put we call it as a capillary barrier layer or, clay cover. It can be, it should be designed properly considering the atmospheric condition, rainfall and all of that. Clay cover, you have many types of clay covers, like, it can be what is the
compacted clay.
Yeah,
Compacted
see,
clay.
you should not use soils. In my opinion, you should not use. Biochar can be used. Right?
Yeah.
Any waste materials. Okay, there's other way that can be done. And after the top of it, you should have, the on the top of the capillary barrier layer. Okay, you can use a drainage layer because we want when rain comes, rainwater should go out. Okay, so we don't want that lot of rain to enter into this clay barrier. Some amount of water is fine, but not too much, right? So better to put a drainage so that it's all diverted. And on the top of it, we'll go for vegetation layer. That's it.
And regarding the drainage layer, people nowadays using maybe geosynthetic drainage layer,
Yeah.
but people earlier can use that sand drainage layer or maybe gravel drainage layer doing that. So
We should not use sand and gravel. So for
drainage
waste,
layer.
we should
Okay.
never use sand and natural materials for landfills. I mean, that should be our motto.
So geosynthetic drainage layer.
Not geosynthetics or any waste materials. Waste plus waste. And everything. Waste doesn't deserve soil, natural soil, aggregates. Okay, that's
Okay,
necessary.
sir, understood, sir. Sir, please continue.
Okay, now I will try to cover something else. 721. Let me share.
You can continue after 7:30 also. 45, if you can, if you want, or if you're okay.
Yeah. Let me
Okay.
just load my presentation.
Hello, sir.
Hello.
Hello, sir. I have a question. Like,
Yeah.
recently, Morth or CRRI, they have given the manual for utilization of solid waste in the road construction.
Yeah.
So, which type of geosynthetic can be utilized so that the durability can be achieved in if we are
It's by
using it
design.
with the solid waste?
Road worker, right? No,
Yes, sir.
see, the MSW they said, and there is a requirement that see the organic content should be minimum, less than 5%, or actually, ideally, organic content should not be there in any of the materials that we're using in road construction. There should not be any organic content material, and it should have a standard specifications for road construction, like it should be well graded and all of that. If it's able to, if you're able to clearly say that it's more like a soil-like material, right?
Yes.
I can't call it a soil because it
Yes.
is from solid waste. But if it is a soil-like material, like it doesn't have any organic content, ideally I don't want organic content. Okay.
Yes.
Then because if it is organic content, there will be settlements. We don't want settlements, right? And
Okay.
definitely for national highways. Okay, it can be for service roads, no problem. But it should satisfy. Then once you say that it's reasonably good soil, you have a geosynthetic design principles which can be used. And it's not like a you can like you are using it for increasing the load bearing capacity or drainage. You can do any products you can use. It's not a problem at all.
Okay. Thank you.
Yeah. Now,
Sir, are you there?
yeah. I'm just trying to, yeah. Okay.
Oh.
I think I will cover one more.
Hmm.
Yeah, I think I will load it. Okay. See, I just want to, am I audible?
Yes,
Hello?
yes, sir.
Yeah, I just, because we have up to what time I have?
Sir, you can continue till 8 if you want.
Okay.
Or if you are exhausted and tired, you can stop, sir. Because
Okay,
you are
this,
busy too much.
yeah. I know, it's okay. Actually,
Hmm.
this, I wanted to explain the reinforced soil principle, which is very, very important. Okay. Um, Then there are factors affecting. I just try to touch upon them. Okay, if possible. Okay. So I just want to explain the principle of reinforced soil, which is so important. Okay. We know about, you're able to see the retaining walls here, varieties of retaining walls. Hello.
Yes,
Uh,
sir.
Yes, sir. Yes,
Okay.
sir, we can.
So yeah, okay. So the thing is that retaining walls or varieties of we have. Say for example, we know about gravity walls, about cantilever retaining walls, and counterfoot retaining walls, and we also know about tieback walls, like where you have a anchoring system and all of that. But we also now we have what is called reinforced soil walls or soil nailing. These things have emerged in most of the applications. Now everybody is doing the same thing. So I thought it may be useful for some of the people here to know about what is a reinforced soil, because most of them are more familiar with reinforced concrete, right? So this is something that one should understand, that similar to reinforced soil concrete, soil reinforcement is a construction technique. Okay. And the main thing that is important here is the friction between the soil and reinforcement. Okay. So, in fact, in concrete and steel, we depend on the bond between the steel and concrete, right? Here, it's soil reinforcement depends on the reinforced friction between the soil and reinforcement. So, this is, in fact, this observation was made by Henry Vidal, who is a French engineer and who was discussing with his who was playing with his daughter in the beach. And this is an example, like, they were able to see that the sand mound, which is reinforced with pine needles, had better, um, stability. What it means is that for the same height, you're able to, the base width is less, or you're able to increase the height of your mound. So that was fascinating to him. And he did a lot of experiments and realized that the friction between the sand and the pine rods or needles, whatever they have, was a contributing factor. So that led to the understanding of the reinforced soil. And so, in fact, there's an example that people tend to show that this material without reinforcement can be destroyed. It doesn't actually, it becomes shapeless. But this one with horizontal layers of reinforcement, he's able to stand on this. This type of experiments are done routinely in many of the labs that we have in the country. All students stand, and then that's a demonstration that how reinforced soil behaves. Okay. So the fundamental principle is that if you want to understand the normal soil, when you apply a load, there will be a deformation, both vertical and horizontal. Okay. Both vertical and horizontal takes place, and it has a new equilibrium, right? So that's sigma 1 and sigma 3. There will be both, both horizontal and vertical stresses would be there because of unfilled soil. But at the moment you put some sort of reinforcement, it can be anything, like even some geograde, geotextile, or any sheet of paper, some which is durable. Okay. What happens is that there is a friction that gets developed and across this reinforcement, and that friction will oppose it. It creates what is called a pseudo confining stress. That is, like, what is happening is that there is a load applied and there is a tendency for lateral dispersion. Okay. It reaches a new equilibrium. But by having this sort of reinforcement, there is a friction that gets developed, and it offers some sort of confinement there. Okay. 1, 2, 3 layers. Say, for example, 3 confinement areas are there. So the applied stress, which is leading to more compression and both vertical and horizontal deformation, is now prevented by this sort of confining stress. You are trying to apply a load, but this pseudo confining stress, we call it, because that's a sum of all these frictional forces that is developing. Okay. So that becomes, that leads to less deformation at the top. Like you can see that the delta V is more here, delta V is less here. And the interesting thing is that delta the deformation is required, and that is required to cause friction. There is a small movement required on this, mobilize the friction here. That's one thing it is. And if you are trying to say that it's a pseudo confining stress, this is what it is. Like normally, this is a combination of in a Mohs cycle. This is a combination of vertical and horizontal stresses, and the soil, it tends to move, and then there'll be some sort of say, for example, the way that we do is that you have a sigma stress, sigma V, and there will be a horizontal stress K naught times at the K naught times. It will come here, and it tends to move little bit. Okay, so that particular thing, there'll be small deformation required, and then you will see that it is still below this failure envelope, Mohr column envelope, and that means that it is again safe state. So that friction, or that friction is quite necessary, and that friction is converted as tensile force in the reinforcement. And it can only slip, if it is a smooth surface. So the way that we do is that it gives some sort of pseudo confinement in the form of additional cohesion, right? So, for example, this is a without reinforcement, there is no cohesion. There's only friction. But if you have a reinforcement, it has cohesion as well as friction. So this cohesion is because of the reinforcement. That cohesion, you can say confining pressure. Okay, confining pressure or cohesion is because of this reinforcement. That makes it to really contribute to additional stability in reinforced soil structures. That's a general understanding. And in the case of reinforced soil, we have reinforcement element, soil, and the precast elements, if at all you're trying to, because the only thing that is important is that the friction, this mechanism should be controlled. In the sense, there will be facing elements. Like in a retaining wall, we put some thin facing elements. That's again as per design. And so the beauty in this technique is that what are the technical benefits, if you want to understand? Like it reduces the forces in the soil that cause failure. Like what is causing failure is that failure is two things: a lot of deformations. But if the moment you put reinforcement, deformations are reduced, and confining stresses are increased. Then other thing is that shear resistance of the soils does not dominate design. Say whatever design practice was there in soils, it's only the C and 5 we are using. Now the tensile strength of the reinforcement comes into picture. So if you understand the reinforced soil behavior properly, and then you should know C and 5, but if you're able to handle tensile forces from the reinforcement better and give a proper design, it's good. The other beautiful thing that we use, what you call technical benefits, is that we know that the soil is poor in tension, poor in shear, okay? Shear or tension, whatever. Even in concrete is poor in tension, right? Actually, the tensile stress of concrete is much less than the tensile strength of soil, okay? People have measured it. And so the shear resistance of the soil is much less. And so if you have a tensile capacity of the reinforcement, that induces additional shear resistance. Okay, what is happening is that the shear resistance is additional, and that is in the form of a tensile capacity reinforcement. And not only that, this becomes a very flexible structure, and it leads to flexibility in deformation, tolerance, and all of that, and it improves the overall performance of the structure. That's what it is. And economic benefits, we have seen that it is a 50% savings, 30% savings minimum. There are many cases, I think other colleagues will maybe discuss. Then the locally available soils can be used, and poor quality soils also can be handled to some extent, in some sense. Okay, land acquisition costs kept to a minimum. It is a very good advantage. Less construction time. Okay, so when I want to explain the principle much better, in a better way. Like, say, for example, this is a failure of here. What happens is that if you just look at this, there is a tensile component of this force. I will explain that in a better way here. Like if you do a direct shear test, you apply some normal force and there's a shear force. So what is resisting this? This thing is a PV tan. So if you want to calculate the shear force, it's PV tan phi. Okay, PV tan phi. And this is like this element of the soil is under tension. Okay, now or it is getting sheared, so we call it, because it's being sheared in the on both the sides, like upon the tendency is that it's a tensile forces generated on the soil element here. Now you put a reinforcement there. Okay, you're trying to put a reinforcement, okay, in some form. So if you're trying to put in a sand, in a complete sand reinforcement like this, there is a component of this. So there will be a friction along the surface, whatever is there is some interaction throughout this box, and there is a component of tensile force that acts in the direction opposite to the shear force, PS. Okay, and then there is additional component that it comes here, normal stress. So PR sine theta, PR cos theta, there are two things. So earlier shear resistance from the soil alone was PV tan phi. Now a reduction in shear force is this one, because now PR sine theta is now in the opposite direction, so it's less. So the increase in the force resisting shear. So earlier the resisting shear force is only a normal force. Now additionally you have additional force here, PR cos theta, and then resolve into the direction, so it becomes overall. So the increase in shear resistance will be this much. It's a beautiful idea that normally it was only PV tan phi earlier. Now the additional resistance shear force is PR into sine theta plus cos theta tan phi. So this is a additional thing, additional benefit that you are getting by putting the reinforcement. What it means is that this is better explained by this diagram, that this is a orientation of the reinforcement. Okay, so the orientation of the reinforcement plays a big role, and for different types of soils, okay, how much is that increase? So you can see if it is if the inclination like 30 degrees or 40 degrees is there, it is in this optimum line, like it is in this range. Very good benefit depending on the friction angle, that there is additional strength increase of some magnitude if it is in this range of 30 to 40, 60 degrees. And so that's what it is. It's a very interesting observation that why this is important is that most of the civil engineering applications or geotechnical engineering applications, the soil reinforcement is placed in this 30 to 60 degrees. Say, for example, if I go back to my previous example of slope, like this inclination, whatever we are mentioning here, that is a range of 30 to 60. It's a good margin, but at the same time, if you look at this thing, it's somewhat flat, not reasonably flat compared to other things, which means that it's consistently that contribution is there with minor variations, and it's good. So that way, the whether it is a reinforced soil slope or the same thing is also possible in a bearing capacity application. If you put that, we know about log spiral failure surfaces on the footing, and if you put a reinforcement across the shear planes, the same angle also operates. Like it can be an angle like 30 degrees or 40 degrees or something. So that way, it's an ideal thing in geotechnical engineering. You want the problems of geotechnical engineering or bearing capacity, slope stability, and many other related things, deformation problems, all of this, all get resolved by having reinforced soil technique. Okay, that's one thing. Okay, then the other thing that we should understand is that the soil behavior itself. Say if it's not a magic solution. You have to compact this sand in a good way. A good dense compacted soil should be there. It can't be loose. Why it should not be loose is that I can talk about in terms of what is called a strain compatibility diagram. Okay, strain compatibility diagram is that which will tell you. See, we assume that now we apply a load on the soil particles will take the load. Now, in the case of reinforced soil and reinforcement together they took the load. So, if the soil is densely compact, so there is a sharing mechanism now, load sharing mechanism, right? So the thing is the soil will take less load compared to reinforcement now because of the friction, right? As I said. So if I say that the reinforced geotextile is stiff, it's good, and if it is flexible, it is different. So depending on the stiffness of the reinforcement, type of soil. If the reinforcement is stiff and the soil is dense, okay, it will have low strains. You can see that the strains are lower here, maybe less than 1% or something. So the strains are lower and it gives very good stress in the reinforcement is mobilized. That reinforcement force in is very good for our design. So that's what starts operating. Okay, but if the soil is loose, what happens is that it will strain is little more. That's what it is. But we don't want strain to be more because that gets reflected in deformations in the structure. So ideally, we need to have a good compacted backfill and good stiff reinforcement if you want very, very low deformations, say for example, a retaining wall. But in some other cases, it can be slightly, we should have a balance, but the principle of strain compatibility should be understood. So this is a reason why this type of soil reinforcement technique has been very, very effective. And there are many factors that affect the reinforced soil behavior that it can, there are a lot of lectures could be given. What factors control design, like what type of, say for example, it depends on the type of clay, it depends on the degree of saturation, it depends on the construction method. There are many methods that are there. So I don't want to go into details, but I just want to highlight the principles of reinforced soil and the geosynthetics that we can have in our engineering practice, that they offer wide varieties of solutions. This is where I would like to conclude. And if you have any questions, you can ask me.
Are there anyone? Dear participants.
Good evening, sir.
Yeah.
Sir, you have talked about the orientation of reinforcement play a significant role.
Right.
So in actual field, how we will manage the orientation of the reinforcement throughout the soil body?
No, see, let me tell you, if you want in the construction of the reinforced slope, we are putting everything horizontally, right?
Okay.
See, the way you're putting this, say you're constructing in the design, you're backfilling, reinforce the retaining wall. You make some 30 centimeters, 50 centimeters and roll it. You put a geogrid, or then again put a soil on that, and then compact it and put a geogrid. When the load is applied, okay, the failure surface I have shown. But the failure surface is in some direction, and it is this reinforcement direction is also in the same way. Like 30 degrees or 60, whatever I showed. That exactly it is not changing anything. Like we are doing our regular compaction practice, and we are putting the geogrid. Nothing else. We are not then again put the soil and compacting like that. We are rolling it. Whatever construction practice that we are doing, we are not really changing. And you see the benefit here that it is not the angle is somewhat natural. Like whatever is happening, we are not taking any special effort, right?
Okay. Yes.
What is the doubt now? Is it clear?
Yes, sir. Thank you, sir. Yes, sir.
Yeah.
Sir, before you leave, I have a little thing to share.
Yeah.
Just 2 minutes. When we were exchanging messages for fixing many things about this FTP, I don't know if you can remember, I mistakenly wrote, "You are my fan." And my daughter saw it. Papa, you are my fan means Sir is your fan. No, it's wrong. Then I wrote, sorry, it's my mistake, sir. I am your fan. Uh, then in reply you wrote, the reverse is also true. God bless you. So by this little thing, what I can understand, you are very good influencer, motivator, and great teacher. So I'm so influenced and so motivated by you. Not only me, my whole family. I have my daughter, I have my son. My daughter is in class 9, son is in class 7. So really, sir, you are great. You're really great. You're so influenced.
Everybody is great.
And that is the main thing, sir, to motivate and to inspire people. Because these are the things what we are doing in FDP. These are all available in YouTube and in many platforms by yourself also from your side. So to have this knowledge, not only is necessary to attend the FDP, but what we need that motivation, inspiration from you, from your face, from your mouth directly. So that is the necessity, sir. So you are
Thank you
great,
so
sir.
much.
We love you, sir.
Thank you so much. Any information, these are all available online, NT and NPTEL courses. Anybody, people who want me to, give some information, I'll be happy to provide. Thank you very much. Thank you.
Yes, sir. Thank you, sir.
Thank you, Dr. Krishna. Bye.
Yeah.
Stop sharing. How do I exit? I don't know how do I exit. You can kick me out. I don't know how do I exit. I don't know.
Okay, sir. I will do.
Krishna.
Okay,
Sir,
okay. Doing, I'm
Thank you
doing.
so much. Yeah, thank you, sir.
thanks.
Yeah.
Bye bye, sir.
Bye.
Thank you, sir. Thank you, sir. Have a good night.